I think the main thing that I try and proceed with forward is, at the end of the day, if you're delivering something that's going to be product focused and is working in a production system, at the end of the day, it's all software, and there's practices that we have for software that isn't relying on empirical processes to develop, like machine learning models, for example, are. And we can begin to look at how we do this for conventional software and try and apply it to those more empirically defined pieces that are so kind of characteristic of the data science development process. And that, just saying that is not easy. Like, this stuff is really difficult to do. Mm-hmm. It's just it's almost like, it's not like the kind of addendum to the data science process where, it's like there's a single step that we then see, and then we put it in production and everything lived happily ever after. Like, in my view, I think this is where almost a whole new discipline is going to develop over the next 5 to 10 years. And it's only now we're starting to see kind of people looking at this in earnest. And there's loads of really, really interesting and cool technologies that people are building, purpose-built for this kind of stuff, from the model orchestration to serving to instrumenting. Like you were mentioning earlier, there was, I think, Glenn, you mentioned like 5 or 6 different things there, from like a serving and instrumentation and testing perspective. And these things are like, these all make intuitive sense for us to talk about from a quality perspective, but the tooling just now doesn't really exist for many of them, which is scary, but it's also really exciting as well.
One of the and maybe tell me if this is like an apt one analysis, and two, whether it's a worthy comparison. So whether it's both accurate and or useful. And so I view software development as essentially a deductive intellectual process, where effectively like A follows from B, B follows from C. And, if you make the incorrect assumptions about, for example, what type of data comes in or something like that, or how people might click or interact with it, you will get errors in your software. However, it is fundamentally a deductive process, where if you can get each layer in turn working as you expect, the outcome will be precisely as you expect. And that typically, when you have errors in these type of software developments, it is because you have essentially a faulty assumption or a misunderstanding about the scope of what you might be asking at any given step. And so that's why I view software development as a deductive process. In contrast, I view data science and machine learning and statistics as it's deductive, inductive, and abductive in the research and development phase. And then the moment you pop it out there, it's hugely inductive. So effectively, you have these different modes of thinking. And by inductive, I mean, like you said, yes, I know that it works under these scenarios. And now I'm going to suspect that it works under the rest of them, or whatever else I throw at it. And so effectively, part of the challenge here is that the scope of error has increased greatly, and beyond just what you could control in a research setting, because obviously you're deploying these. There's a difference between, for example, when I was a statistician in the Oxford hospital system, saying, here's the model, here's what I found, here are my results, here's all this extra bit, hand it off to a lab scientist or clinician, and they used it. Very different from saying, like, okay, here's my thing, time to just launch this into space. Yeah. Or alternatively, I'm going to put this on your space satellite, and it's just going to do its thing. Don't worry about it. And so I think those are two different processes, and I think it is very helpful for people to make the distinction about why precisely these things are breaking down.
I think that is a very useful way of describing the contrast between the two components that are now. I think the thing is, these components are having to now live together. I think this is the kind of key point, is we've now got these two kinds of components that now live in the same world. And I would actually say as well, if we go back to just like the traditional software stuff, it being deductive, that makes it seem very, I mean, when you look at testing a software system at the smallest kind of unit of a like a function, or just the smallest kind of like logical way of analyzing a piece of the system, it seems almost trivial to folk who haven't necessarily worked as part of larger systems. And from a development perspective, yes, everything's very crisp. From like an inferential perspective, we have to, if you put input A in, you're always going to get output B. So in that sense, it's very, very deductive. But the challenge is when is when the kind of combinatorical like explosion of stuff happens when you begin putting these bits together, and you get multiple players who are acting on the system at any one time with their own requirements from a development perspective. They have their own biases from a development and design perspective. I mean, in many ways, a software system is kind of like a huge living document of like prepositions and then outputs, and to then 100% is deductive, but it becomes, I wouldn't say quite chaotic, but it becomes really difficult to keep a track of what's happening when those deductions are being altered and tested in different ways, hundreds of thousands of times, depending on obviously the complexity of the software that you're developing, which is why testing becomes so important for even just conventional software. It's something that it makes our assumptions about the component parts and the system as a whole, it makes those clear, and they're tested rigorously as part of a continual cycle that ensures that we don't introduce problems when we make a change. Which makes for anyone who's from the software background, this stuff will all be very familiar. There's debate about how central testing should be to software practice, because obviously it has some effect on the velocity that you're able to write code at if you're having to write tests at the same time. And there's a lot of cargo cult stuff where people say this is the way to do testing, or this is the way to not do testing, or we don't need tests at all, we'll just do it. But broadly, I think people would agree from a software background that testing is at least useful in a wide variety of cases. But the very interesting thing to me is that if you take that purely deductive set of components that are complicated in the way they're intertwined and codependent, and then you are testing those to make sure that things are okay from like a base case perspective, and then we're adding this inductively designed and derived component into the mix there, that just adds so much more complexity to the area, which again is scary, but it's also is very interesting from like a kind of challenging technical perspective to try and see how we make these two components play nice together. Because often when we take like our predictive models, say, that can be deployed as like, okay, a user comes along and they ask the model in some format for a prediction about their input, and we get the input back. I mean, that's fairly ring fenced and independent from, let's say, the API components that serve the infrastructure around about that artifact. But increasingly what's happening is the inductively designed data science and machine learning components are becoming parts of the pipelines of software more broadly. And when your output from like a machine learning model is an input to another potentially very complicated piece of software, then goes away based on the output to kind of like come to some other conclusion, to provide some other action to another software system, and you scale that up across. I mean, nowadays, when you look at software systems at the top level of an architecture, if you look at things like microservice architectures, these are very complicated systems at the highest level. The potential for uncertainty to be introduced to these systems is enormous, and that's just the integration part of that. Like that's not even thinking about all the stuff we've just talked about for the last hour from the perspective of the uncertainty behind developing the component from a data science perspective in the first place. So there's a real kind of coming together of these two cultures, I think. That there's a lot of work to try and to make these two things play nice, because truly, I mean, it's really exciting like what we can potentially do and what we're doing already with data science and in production. I mean, there's so many products that, I mean, to somebody who's not necessarily data literate, some of this stuff seems like magic. The idea that you can have something as simple as like a takeaway menu for a local, like, or like an Indian takeaway that wasn't necessarily like on your radar before, recommended to you based on like your preferences of food orders over the last 6 months. Like that seems, to somebody who doesn't understand software and data, that seems like it's unthinkable that would happen. Something as benign as that would happen 10 years ago. So the outputs of this, I mean, obviously that's before we even get into the topics of like the areas that you've obviously been working in from a medical perspective. Some of the stuff that we can do with this is going to have a huge impact, and is already having a huge impact on the world, kind of writ large. But it's making sure that we do it the right way, and we don't introduce all sorts of crazy uncertainties into our already pretty difficult to track software systems more broadly.
Yeah. So maybe just to summarize this last bit. So obviously we've described the software development. We've described software development as a deductive process. However, that does not mean that it's straightforward or
I
unchallenging
think
or simple.
Yeah,
because it's like it's essentially you can have a large number of simple mechanisms, and when you put them all together with all their own assumptions, then immediately can become an extremely complex problem. So sort of like you can have a system, and depending on what your initialization points are and things like that, you can immediately have something that spins off into something very strange.
Yes, yeah.
And also some of the challenges of that when you have to bring multiple deductive systems together. If there is a conflict or a contradiction between any one of those components, that might only arise in an extremely rare case, one that you might not, for example, think about with all the other work that you have to do and things like that. So it's not to call these systems uncomplex. They're highly complex. They're highly complex in a certain way. Yeah. And perhaps they're so highly complex in a specific way that the nature of that system is now effectively, on some level, somewhat of an inductive system, and things like that. So, yeah, there's a lot there. It's sort of like, those little things where you drop a ball and hits one peg and then the next peg and next peg. Each of those individually is like a small piece, and it's a very straightforward, simple process. But when you put them together, you can imagine the variety that can be created, and enumerating those across multiple dimensions, across the variety of each of those dimensions is quite difficult.
Well, one interesting point, actually, I've never looked into this, but I might have a look at this evening after this call. But whether anyone studied software as a complex system from like the formal definition of complex systems, because it seems to me, as a layman in that aspect of complex science or complexity science, that it seems like that would be the case. And the point we're getting to is that by adding these new components into it, the complexity is even greater potentially as well.